Hello everyone, it is a great honor to share our work new towards efficient, fully homomorphic encryption acceleration using Tensor Core with you today. I am Dian Jiao, a master's student at the Institute of Information Engineering, Chinese Academy of Sciences, advised by Professor Rui Hou and Professor Mingzhe Zhang. Our work new achieves significant efficiency improvements for FHE by deeply exploring the hardware potential of GPGPU, especially the computing power of Tensor Core. Next, I will introduce the background challenges, solution design, and the experimental results step by step. The core advantage of FHE is that it enables computations on encrypted data without decryption. Practical applications include medical research and financial risk assessment. However, FHE faces a fundamental challenge. Its security comes at the cost of computational efficiency. This renders FHE computations 100,000 to 1 million times slower than plaintext operations, creating a significant barrier to practical adoption. So, why is FHE so computationally expensive? Let's break this down from both algorithmic and hardware perspectives. On the algorithm side, FHE uses lattice-based cryptography. This requires hefty computation for operations like polynomial multiplication and modulus reduction. On the hardware side, traditional CPU scale architectures can't handle this scale of computation. Even moderate FHE inference tasks might take hours on the CPU. Looking at other hardware acceleration options, ASICs have high development costs and lack flexibility for rapidly evolving FHE algorithms. FPGAs also have drawbacks, such as limited on-chip memory bandwidth. This leads us to the third option, GPGPU, which offers a promising balance of cost, flexibility, and performance. GPGPUs are widely used in existing data centers, making it easy to integrate FHE workloads without costly infrastructure upgrades. In terms of flexibility, GPGPUs with their software ecosystems such as CUDA can quickly adapt to these new algorithms through software updates, eliminating the need for hardware redesign. Performance-wise, modern GPGPUs like NVIDIA A100 or H100 offer massive parallelism with thousands of concurrent threads, perfect for the parallel polynomial operations in FHE. They also feature high bandwidth memory, providing over 1.5 TB per second, fast passing FPGA's bandwidth. NIO's design is closely tied to the Tensor Core architecture in GPGPUs. Tensor Cores introduced by NVIDIA in the Volta architecture in 2017 were originally designed to accelerate matrix multiplication. In NVIDIA A100, the FP64 Tensor Core delivers a theoretical performance of 19.5 TFLOPS, more than double that of the CUDA cores. However, existing GPGPU-based solutions like TensorFHE fall short in utilizing Tensor Cores, especially the floating point components. This underutilization is precisely what NIO aims to address. The first challenge we encountered is the word size issue. In FHE, the word size refers to the bit width of the modulus after RNS decomposition. To meet the precision requirements of FHE applications, the original 32-bit word size is no longer sufficient. However, increasing the word size leads to a significant rise in hardware computation overhead. This is because larger data types result in higher computational and I/O costs, and also increase the number of splitting and merging operations required for multi-precision computations on Tensor Cores. Our key insight here is that there is a trade-off between algorithmic complexity and hardware implementation complexity. This trade-off is influenced by the word size. The key LLS method transforms polynomials from the original modulus space to a new modulus space T. And the word size of the modulus space T is referred to as word size T, which can be chosen manually. There is an inverse relationship between word size T and a hyperparameter alpha tilde. A smaller word size T reduces the scale of multi-precision computations, but increases alpha tilde, leading to more operations in key switch. Conversely, a larger word size T reduces the number of operations, but increases the complexity of multi-precision computations. Therefore, careful parameter tuning is essential to balance these two aspects. Moving on to the second challenge, focusing on computational kernels. In the CKKS scheme, there are 6 basic kernels, with base conversion in the product and NTT being the most heavily used. We've noticed that the standard computation process for base conversion and in the product uses element-wise multiplication. Each polynomial coefficient is accessed multiple times, but these accesses aren't contiguous. This leads to poor memory locality and low data reuse, as shown in this figure. Base conversion and in the product account for a large proportion, especially under the key LS method, where they correspond to the upper bars in this figure. This inefficient memory access pattern significantly impacts performance. Since base conversion and inner product involve element-wise multiplication and accumulation, we realized the computation can be transformed into matrix multiplication. Matrix multiplication has good data locality, and by this way, we can enhance data reuse. The third challenge is that existing solutions underutilize tensor cores. They only use the int-add components to accelerate the entity kernel, leaving the floating point components idle, and other kernels besides entity are not accelerated by tensor core. However, our analysis shows that int-add isn't the best choice. In A100, integers are only supported up to int-add, and floating point numbers up to FP64. This means large numbers need to be split to ensure computational accuracy. As shown in this figure, FP64 components are 1.6 times faster than int-add components at 36-bit word size and 1.7 times faster at 48 word size. This proves that leveraging floating point components can enhance tensor core efficiency. Additionally, we can also accelerate the kernels converted into matrix multiplication using tensor core. Let me now introduce one of the key designs in NEO, algorithm and data optimization. The original approach of base conversion and inner product kernels used element-wise multiplication, which led to redundant data access. Take base conversion, for instance. Each polynomial must be multiplied by alpha prime conversion factors with no data reuse. We have restructured the computation by transforming it into matrix multiplication. By reordering the polynomials and conversion factors, we have converted the element-wise multiplication and accumulation into a single matrix multiplication. This way, all data is accessed just once to complete all necessary computations in one go. Specifically, in terms of algorithm transformation of base conversion, we reorder the input data from the original alpha times batch size times n format to n times batch size times alpha. We then perform matrix multiplication with an alpha times alpha prime base conversion matrix. This allows all data to participate in the required computations in a single matrix multiplication. From the pseudocode, you can see that we have introduced the pre-processing and the post-processing steps to handle data reordering and restoration. Experimental results have shown that this additional overhead is minimal and barely affects overall performance. The second key design is the in-depth utilization of Tensor Core's floating point components. As shown in this figure, when using int-add components to handle 36-bit word size, each number must be split into 5 slices, resulting in 25 matrix multiplications. Moreover, Tensor Cores impose fixed fragment shapes for different data types. For instance, int-add matrix multiplication has minimum fragment shape like 32 times 8 times 16. After transforming base conversion and inner product into matrix multiplications, the key dimension is relatively small, like 4 on the common parameters. This means the input data cannot fill the minimum fragment, requiring 0 padding for unused parts to be added. In this figure, fragment A has a key dimension of 16, but only 1/4 of it contains valid data. The remaining 3/4 of the matrix multiplication involves invalid computations, severely reducing int-add component efficiency. In contrast, FP64 type supports 53-bit precision, so 36-bit data only needs to be split into 2 18-bit slices. FP64 components also supports fragment shape of 8 times 8 times 4, which can be fully occupied by input data without any padding. This avoids the efficiency loss caused by invalid computations. As a result, FP64 components of Tensor Core may be a better choice. Our third design is the optimized kernel mapping strategy. It achieves a better allocation of computational resources for the CKKS scheme. We map the basic kernels like this. Kernels transformed into matrix multiplications, base conversion, inner product, and NTT are mapped onto Tensor Core FP64 components to leverage their matrix computation efficiency. Simpler non-matrix kernels like mod-add, mod-mul, and auto are mapped onto and as well as data reordering and bit slicing and merging are mapped onto CUDA cores. Additionally, since the key dimension in inner product varies with computations, we only use the Tensor Core when valid matrix multiplications reach at least 80%. Otherwise, inner product runs on the CUDA cores. Beyond mapping strategy, NEO combines general GPU optimization techniques like kernel fusion and multi-stream processing to parallelize work across Tensor Core and CUDA cores, boosting overall GPU component utilization. In the experiment section, we first introduce the system configuration and parameter settings. We use servers equipped with an NVIDIA A100 GPU with 40 GB of memory. For parameter settings, we adopt typical parameter sets based on the CKKS scheme. To ensure a fair comparison with the previous work, we have configured 2 consistent sets of parameters for performance comparison with Tensor FHE and HE on GPU. Now let's look at the performance advantages of NEO in practical application. The 3 major applications are pack bootstrap, a ciphertext bootstrapping operation that restores security levels and integrates double rescale to ensure precision. HELR, privacy-preserving machine learning based on logistic regression. And ResNet, encrypted CNN inference of different scales. In these applications, NIO delivers strong performance gains compared to Tensor FHE. NIO achieves an average speedup of 3.28 times, and compared to H on GPU, NIO is 1.2 times fast on average. In the most critical and time-consuming operation, key switch, NIO's performance boost is even more pronounced. NIO achieves an average speedup of 4.58 times over Tensor FHE and 2.46 times over H on GPU. Let's further break down the performance improvements of the three key kernels, which serve as supporting results of the application performance enhancements. For base conversion and inner production, through algorithmic and data layout optimizations, global memory transfers are reduced by about 2/3, combined with tensor core acceleration. The throughput of base conversion and inner product is increased by about 2.7 times and 2.6 times. From the figure lower, it can be seen that the pre-processing and post-processing introduced by the algorithmic transformation account for a very small proportion of the total kernel execution time. Even when combined, they are still much faster than the original kernels. For NTT, the optimizations include applying a radix 16 NTT to further decompose the computation and reduce the total matrix multiplication workload. By shifting the computation from int-add components to FP64 components, the throughput of NTT is increased by 3.7 times. Through a sensitivity study, we identified the optimal parameters for KRS method. We found that setting alpha to 5, denominator 9, and word size to 48 maximizes key switch performance. We also conducted an ablation study. First, we applied the KRS method to reduce key switch complexity. Second, we optimized the base conversion and inner product algorithms and data layouts, reducing memory accesses by improving data reuse. Third, we implemented a radix 16 NTT, which breaks down large matrix multiplications. Lastly, we utilized Tensor Core FP64 components to fully leverage hardware power. Each step delivered noticeable performance gains with a combined boost of over 3 times. Okay. In summary, NIO provides an efficient solution for speeding up FHE on GPGPU by combining algorithm and hardware optimization. Our main contributions are 4 key points. First, NIO transforms key kernels from element-wise multiplication to matrix multiplication, improving data reuse and making better use of Tensor Core. Second, NIO uses Tensor Core's floating point components, reducing the overhead from the excessive bit slicing and large-scale multi-precision computations that came with the previous int-add approach. Third, NIO includes the KRS method. By carefully choosing parameters like word size, it balances algorithm complexity and hardware efficiency, ensuring top performance in key switch operation. Lastly, our experiments show that NIO performs very well. It runs over 3 times faster than Tensor FHE on average across different real-world applications on NVIDIA A100 GPGPU. NIO has made solid progress in advancing privacy computing toward real-world applications. Thank you for your attention, and I look forward to any questions you may have.